All right, let's suppose that A and B, let's suppose that P of A is bigger than 0 and P of B is bigger than 0, and that A and B are mutually exclusive. Okay, so P of A is bigger than 0, P of B is bigger than 0, and A and B are mutually exclusive. Can A and B be independent? No. Right. Heuristically, if their intersection is empty, and I learn that B happened, I know that A did not happen. Right? The intersection is empty. What's the Venn diagram for that look like? Right? It's yes? If I learn that A happened, I know B didn't happen, and vice versa. If I learn that B happened, I know A didn't happen, because they don't have any elements in common. Right? So if two events are mutually exclusive and neither has probability 0, they can't be independent. Right? Mutual exclusivity and independence are different and, in fact, incompatible. Right? So this is really, it's like you will be tempted to confuse mutually exclusive and independent. Don't. All right. Where do I want to go with this?
Could you give some examples of closing points or something?
Some examples, sorry?
Like dice or something. I don't know.
Dice? Oh, okay. So let me use a. Let's suppose that we are taking as a model for probability area. So we're looking at Venn diagrams, and we are saying that the probability of an event is the area of the event. The probability of the subset is the area of the subset. So here's S, here's A, here's B. We just showed that at one extreme, if A and B don't intersect at all, and let's just keep the assumption that neither of them has 0 probability for now. Okay. If they don't intersect at all, they're not independent, right? They're dependent, because the probability of A intersect B is 0, and that's not the probability of A times the probability of B, because probability of A times the probability of B is some positive number, because probability of A is positive and probability of B is positive. Okay, so in this situation, we've got probability of AB is less than the probability of A times the probability of B. Right? In fact, it's 0. Yep. Let's have them intersect a little bit. Okay? The probability of the intersection is going to grow. It's going to be less than this for a while. When they overlap by just the right amount, the probability of A intersect B is going to be equal to the probability of A times the probability of B. And then, as they intersect more and more, the probability of A intersect B is going to be bigger than the probability of A times the probability of B, until eventually one of them is a subset of the other, and the probability of A intersect B is just, for the sake of argument, the probability of B if B is the smaller event. So we have this range of possibilities from the probability of A intersect B being 0 on up to the probability of A intersect B being whatever the probability of the smaller event is. Somewhere in that continuum, they overlap by just the right amount to make them independent. Right, so what does that look like? Okay, so here is our Venn diagram again, and this is representing the probability of an event by its area. So A, the area of A is 30% of the area of S, and the area of B is 20% of the area of S. Right now, their intersection, their overlap, is the area of their overlap is 17.2%. What does the area of their overlap need to be for them to be independent? 20% times 30%, which is 6%, right? Okay, so I need to make them independent. I've got to find the place where they overlap by exactly 6%. So in this configuration, they're independent, right? But I'm on a continuum that ranges from probability of A intersect B being 0, if they don't overlap at all, growing, 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 until at some point they're exactly independent. And then it can grow more and more and more until the probability of their intersection is the probability of the smaller event. Okay, so independence is a very special relationship. Now I'm going to have trouble dragging them out without doing something like that, where they overlap by just the right amount. So what is that right amount? It's basically saying that the area of the intersection is to A as the area of all of B is to S. Or conversely, the area of the intersection is to B as the area of all of A is to S. Okay, so it's really, what's conditional probability? It's this area, so conditional probability of B given A is the probability of the intersection divided by the probability of A. For that to be the probability of B, that ratio, this area to this area, has to be the same as the ratio of this area to this whole thing. Okay? And similarly, probability of A given B is this area divided by that area. And for the events to be independent, that divided by that has to be the same as this divided by this. Okay? Very special relationship.